Welcome our next speaker, Tobias Susetzky from TUM. And the title about this presentation is a Holistic Time-Aware Classification Model for Multimodal Longitudinal Patient Data. Welcome.
Thank you. Good afternoon. I'm glad to introduce you today to our holistic time-aware classification model for multimodal and longitudinal patient data. Our goal was building a model to do clinical assessment like a doctor would do it, taking into account all the data a patient accumulates over a long time. This comprises not only numeric data such as medication, lab values, or vital measurements, but also imaging data and textual reports. We don't want to consider these modalities only at one single point in time, but over a long sequence, over a period of time. Therefore, it is especially relevant that the model is also time-aware in order to be able to assess relevancy to all these different items in this so-called multimodal electronic health record. Integrating large amounts of patient journeys, patient history, appears especially relevant since in real-world datasets such as MIMIC, we see that patients very often only have a small number of EHR entries or events actually occurring during their current hospital stay. In comparison, their history, their patient journey is much richer on information. Therefore, our model should not only include the current data, the current patient condition from the actual current stay, but also incorporate the history as a context. The intuition is that the model then should intrinsically learn to assess relevancy to the different items itself, while obtaining an overall impression of the patient for clinical assessment. So how do we do this? First, we arrange all the information from our multimodal electronic health record in a joint, temporally ordered sequence. And we consider every item an event, an isolated event at a certain point in time. Every numeric measurement is an event, every text, even an image is one event at a certain time point. So we represent those events by uniform tokens with additional temporal information. Once we have this sequence, this representation scheme, we want to leverage a huge amount of data and also somehow foster structural learning on this multimodal health records, on these multimodal sequences. So we pre-train a transformer model in an unsupervised way using mask sequence modeling. Finally, we use the transformer encoder and train it for a specific clinical assessment task. To include entire patient journeys at this point, we add a summarization mechanism to incorporate even very long sequences as a whole. Now let's dive into detail about each of those steps here. When constructing the multimodal token sequence, we want to come up with a very flexible representation scheme that can integrate all this highly heterogeneous data of our multimodal health record and is natively processable by a transformer in an optimal way. So every event is represented by a token being the sum of embeddings for type, value, and time and position information. We use relative temporal and positional features to construct a sinusoidal embedding, but in a multidimensional way. For the value, we leverage external pre-trained encoders for imaging and text so that we can obtain semantically meaningful embeddings. For numerics, we use Fourier features. When it comes to type information, in the real world, we will often have data that does look like this. So we have items that are semantically highly similar, yet not syntactically identical. Nevertheless, we want to come up with a representation that is, that is kind of robust to the free text noise that can be introduced here and is also applicable to novel data such as novel drug names out of the box. Most of all, it has to be able to be used in a computationally feasible reconstruction of this information later in our mask sequence modeling. So we solved this by, or we achieved this by splitting type information into a high-level category. We define manually a small set of those categories, such as lab value or vital measurement, and type specifics, which can be free text, for instance, a drug name. So for the category, we then use a regular, fully trainable embedding layer, while for the specifics, we again employ a domain-specific LLM, providing us semantic validity out of the box. Having constructed our sequence like this, we then pre-trained a transformer using mask sequence modeling, so we can use large amounts of data while jointly learning across all modalities and time points. For this, we apply a sliding window to all the patient timelines that we have in our data set to obtain fixed length subsequences. At training, we mask a considerable amount of those tokens in each sequence in a biased random fashion, counteracting the natural imbalance in type category frequencies. The model is then tasked to reconstruct the masked tokens from context. In particular, it should reconstruct the fixed embedding components via the MSE, and we add a classification head to reconstruct the type category. Finally, we use the transformer encoder and train it for a specific clinical decision-making or assessment task. So we add a CLS token to the input and a head to the model. But we also wanted to incorporate, to accept as an input entire patient journeys, which can be very long. So we want to represent the long tail data only by very few tokens, so summarizing them. For this summarization, we apply our model piecewise, iteratively. For each subsequence, we obtain the model's output features as a summary representation. We then add a trainable dedicated type token to those summaries to mark them as such. Then those summaries are appended to the most recent tokens in the sequence, which we leave unchanged. And now this much smaller or somewhat condensed sequence goes into the model again to obtain the overall features for the task-specific head. Note that this entire setup is still trainable end-to-end and enables processing very long patient journeys in a computationally feasible way. We train and evaluate our approach on a merged version of the MIMIC dataset, leaving us with more than 400 million single events from roughly 300,000 patients. We do this for pretty common clinical decision tasks such as length of stay or readmission and survival. For all our experiments, we always include the most recent data since the beginning of the current stay, up to 12 hours, also limited by any event that might reveal the prediction target in advance. We then experiment with including additional amounts of patient history, different extents of context, and observe the impact on the model's performance. We see that, for instance, for hospital length of stay, we achieve best performance when including 6 months of patient history, compared to having, for instance, no history at all. We see similar effects when it comes to in-hospital survival and hospital readmission. However, for some tasks such as ICU length of stay or predicting triage acuity in the emergency department, we see that short-term or most recent data appears to be more relevant and to be used more effectively when not being cluttered by long-tail history. In this table, we got the results by training models from scratch, and from here we identified the best performing time span for each task, and then continue to the next step, comparing it to a pre-trained variant. Oops. Yeah, and what we see overall here is what I already mentioned, that history actually matters and impacts performance. So we pick the best performing time configuration for each task and compare against the pre-trained variant. And here we see that pre-training on a very large scale, but only for very few epochs, already slightly improves the performance across tasks, while we achieve state-of-the-art performance compared to our baselines. So to wrap up our approach, what did we do? We put all historic and current patient data onto one joint timeline, arbitrary length, and composition of modalities, no constraints imposed on sampling or missing data handling. We squeeze everything into a transformer and learn jointly from all time points and modalities at once. By this, we improve clinical decision making, and we show that patient history actually matters, impacts the model's performance, and often improves it. Thank you for your attention. I'm really happy to dive into detail in the poster session right afterwards, and right now I'm curious to take your questions. Thank you.
Thank you.